Hey, everybody. Really glad that you could join us here today. I'm Kenny Stoltz. I'm a product manager on Ware, and I lead product for some of the standalone and iOS features.
And I'm Griff Hazen. I'm a software engineer and tech lead for Ware's developer platform.
So both of us have been working on Android Wear since before 1.0. And today, we're going to take you through a couple of the things that you'll want to consider when you're designing and building standalone apps in Wear 2.0. OK, so first, a question. Why would you build a standalone app? There are 3 reasons, and the first is the most obvious. Sometimes you just don't have your phone with you. Running is an obvious use case where you might want not to have some phone strapped to your wrist, and a bunch of other fitness scenarios are similar. But Standalone offers the opportunity to free you from your phone in a lot of other situations that you might find yourself in throughout the day. So if you run to the store and you forget your phone, if you're doing chores around the house, you don't want to have it in your pocket, if your phone dies, et cetera, Standalone will let you still use that small screen on your watch between the times when you've got your phone with you. Second, is that building standalone apps is a lot more like building mobile apps. It's particularly faster and easier to build them if you already have an existing mobile app. So you'll spend less time rewriting the basic infrastructure for your app, which means that you can spend more time making your app better on wearables. The last reason is that standalone apps will work on watches connected to both Android and iOS devices. So you want to make your app you want to offer your app to as many people as possible. And if you follow the design patterns that we'll share with you, you can write one wearable app that will work on watches connected to both devices. OK, so now we'll go through a couple of things that you'll want to consider before you start coding. So first of all, what should a standalone app do? The easiest way to start is to think about what your phone app does and then distill that down. So think about what the most important tasks that your app allows the user to accomplish, and then what flows are absolutely necessary for the user to go through in order to accomplish those tasks. Now, you want to think a little bit about your user and how they'll be using your app. They're likely to be on the go, so you don't want to hold their attention for too long, and you want to make sure that you're making it fast and easy to complete those tasks. Keep in mind that you don't want to let the user get halfway through a task and then ask them to switch from the watch to the phone. First of all, obviously, they might not have their phone with them. And second of all, they might get frustrated or lose their place. So you want to try to support every flow that you can from end to end on just the wearable. That said, your user often has 2 awesome devices with them at the same time. So it's great to make the 2 work in harmony and have appropriate and useful content on each screen. The data layer APIs that we released with Android Wear 1.0 will continue to work, and you can use those to build multi-screen experiences with Android phones. Finally, you want to consider both types of phone that your user might have while they're using your app. So Wear 2.0 Developer Preview will allow you to pair with an iOS phone. Once you've paired with the phone, you can sideload your app onto the watch and then test it. There are performance differences, particularly the amount of bandwidth that you'll have, so you really should test. And it's a great way to make sure that you've got a standalone app.
If you're already familiar with how to architect an Android phone app, you'll be glad to learn that Wear apps can now be written in a very similar way. Sure, the user interface may need to be scoped down to the most important user flows and the limited real estate, but the underlying code and services can be written in the same way and even shared between phone and Wear apps. You can access the cloud in the same way, use similar authentication methods, and the same cloud-to-device messaging. Let's dig into a few areas where we are providing additional help for standalone apps. We'll also go through some Android APIs you may be familiar with on the phone and how they can be applicable and useful in Wear. First off, we'll take a look at how standalone Wear apps can communicate with cloud services and store data. One of the most important platform changes to enable standalone apps is the expansion of direct network access, where apps will now be able to communicate directly with cloud services and can also schedule background work that requires network access. When the phone is connected over Bluetooth, network traffic proxies through the phone's connections. When the watch is outside of phone range, Wi-Fi and cellular networks are used, depending on hardware support. The Wear platform takes care of the transitioning between networks. In existing wearable apps, data stored in the cloud was often relayed to the wearable via an Android app on the phone using data items in the wearable data layer APIs. The wearable data layer is still useful when coordinating between watch and phone, but with Standalone, it may be simpler to go directly to the cloud for many use cases. In addition to simplicity, it also works when the phone is not available or when paired to an iOS device. When talking to the cloud, you can use protocols that you're already familiar with, like HTTP, TCP, or UDP. Once your data is fetched, you can store it locally on the device, just like on phones, using shared preferences, SQLite, or internal storage. If your Android phone app is well-maintained and tested, you may be better off starting from your existing code base and cutting things out as opposed to starting from scratch. Common code and services, like your networking, data model, and business logic, can be shared between your phone app and Wear app using a shared library. Form factor-specific code and resources can remain in separate build flavors for phone and Wear. This type of structure is already supported natively in Android Studio and Gradle. When fetching data from the cloud, it's important to fetch only the data that your wearable app will need. Otherwise, you may introduce latency, memory use, or battery use unnecessarily. In some cases, for example, when over a Bluetooth LE connection, your app may have access to just 10 kilobytes per second of bandwidth. We recommend auditing your network traffic, both requests and responses, for extra data that perhaps was only intended for phones. Shrinking large images server-side before sending them to the wearable is another great way to reduce network traffic. In Android, background services are a powerful tool, but should be used wisely in order to preserve battery life. In Android 6.0, Doze and App Standby resulted in significant improvements to battery life by allowing devices to enter a deep sleep when idle or stationary. Doze has been extended in Android N and Android Wear 2.0 to enable some lighter optimizations whenever the screen is in low-power ambient mode or off. Here's an overview of the new Doze lifecycle. After the screen turns off or enters ambient mode for long enough, lightweight Doze can kick in. During Doze, background tasks may be deferred to execute during periodic maintenance windows. If the device later becomes stationary for long enough, a deeper Doze mode kicks in, similar to Doze in Android 6.0. To ensure your background tasks are executed as desired, it's important to write them in a Doze-safe manner. The Job Scheduler API allows an app to register for Doze-safe code execution and is recommended for background work. Various constraints can be selected when scheduling jobs. For example, the need for connectivity, device charging, or periodic execution. It's important to be conservative when scheduling jobs and to avoid execution in ways that could adversely impact battery life. Jobs scheduled with the Job Scheduler API use the Job Info Builder object to provide constraints and metadata. We'll go over a few useful constraints that are available. To request networking, use the setRequiredNetworkType method and specify any or unmetered. Network type unmetered is appropriate choice for large data transfers, while network type any is more appropriate for smaller transfers. Note that in Wear 2.0, some low bandwidth networks like Bluetooth LE are considered metered. To schedule a task that requires the device to be on the charger, use the setRequiresCharging method, or to be currently idle by calling the setRequiresDeviceIdle method. Using both of these together can be useful for lower priority background work or synchronization. Here's an example of a job being scheduled that requires unmetered networking at the time the job is run, in addition to the device being on the charger. Job Scheduler will activate My Job service when both of these constraints are met. The builder method, setExtras, can be used to provide additional metadata. This bundle will be passed to the job when executed. Note the myJobID value passed to the JobInfoBuilder constructor. This is an application-specific identifier. Subsequent calls to cancel jobs or create a new job with the same job ID will update the existing job. Here is an implementation of a job service to handle the job from the previous slide. When the job executes, the onStartJob method is called with the job parameters object passed in. The job parameter object allows you to get the job ID and also any extras bundle provided when scheduling the job. The onStartJob method is called on the main application thread. So therefore, if any expensive logic needs to be run, it should be pushed to a separate thread. In this example, an async task is used to run code in the background. Once your work is completed, call the jobFinished method to notify job scheduler that the task is done.
OK, so now we'll go over a couple of different options that you have for authentication. The reason that you need to start thinking about authenticating is that now your app is running entirely on the wearable. So whenever it makes a request to the cloud on behalf of the user, it's going to need to have a valid auth token that shows that web service that it has access to that private data. But before you rush to ask the user to log in, please consider what you can do with an anonymous user. You want to try to avoid authentication where it's not necessary. And if you need to record data, you should try to record it locally instead of writing it to the cloud by default. You have to remember that the user might not have access to the network at the time when your app is running. Finally, when you do need to authenticate the user, you want to focus on the fastest and easiest methods from the user's perspective. So the simplest way from a developer perspective is the same as on the phone. You can create a login activity, and you can ask the user to type in their username and password. Now, this activity is a normal activity, and if it has an input field with the input type text password, then Where 2.0 will show a special password-style keyboard that will allow the user to type in their password on the watch. Now, this keyboard is optimized for the watch, but it is still very small, so you should try to keep from having to show that keyboard where you can. A couple of ways that you can do that, which are better and avoid that typing, are to use our sign-in technologies like Google Sign-In or Smart Lock for passwords. So both of those technologies use the existing authentication that the user already has to Google and exchange that for a token that's valid for your web service. Smart Lock for passwords, in particular, is very simple to add to your existing client app. It only requires client-side changes, and it works with existing users who've already registered using whatever IDP they're using. So both of these options will be available in some future developer previews that we'll be releasing throughout the summer, so please keep an eye out. So if you're familiar with writing where on the data layer, you might have already thought of one way that you can get a token over to the watch. That's to request that token on the phone and then pass it over to the watch via the data layer. So this method has some benefits. It's fast and easy for the user, but it may have some problems if your auth provider doesn't like the fact that you're requesting a token for the watch on the phone, so a token that's destined for a different device. It also does require the user to have their phone with them and have it on and connected when they're running your app. And finally, it doesn't work on iOS. So if you do choose to use this method in your app, make sure that you have at least one backup method that does work. So one final method that we'll also be bringing to a future developer preview is the ability to open an OAuth URL on a phone. So this OAuth URL points to an OAuth 2.0 authentication service. The user will then switch to their phone, follow through the OAuth login flow, and then when they complete, the auth service will return a token destined for the wearable, which is sent via a callback to the same call that you used to open that URL. So this option will work on iOS, but it does require the user to have their phone with them when they need to log in. So there are a lot of options here. So here's a quick table showing some of the trade-offs. As you can see, Google Sign-In and Smart Lock for passwords both work if the watch is connected or disconnected from the phone, and they work on iOS and Android, and they're fast and easy for the user. The middle two options both require the user to have their phone with them, and the final option is a good fallback option if all else fails. So if you follow along with the previews, we'll be sharing these methods throughout the preview cycle, and that'll help you to build apps that are as fast and easy to log on to as possible.
A third area of focus for standalone Wear apps is how to retrieve notifications from the cloud, either for display to the user as data for your wearable app to use. Google Cloud Messaging, now known as Firebase Cloud Messaging, or FCM, is now supported by Wear. FCM allows you to push data and notifications directly to Wear devices from the cloud. Example uses include delivering sync tickles, small data payloads, and user-visible notification. It works well with those and is cross-platform. The same reasons to use this service on phones apply to standalone Wear apps. It's the recommended way to push events to watches. To send messages using FCM, first collect a registration token when your wearable app runs, and include it as a destination when posting messages to the FCM REST endpoint from your server. Those messages will then be delivered to that device. FCM messages can include two types of payloads. Here's an example JSON-formatted message that will deliver a user-visible notification directly to the stream when received by a Wear device. When the user taps this notification, your app is launched. The second type of payload is a data payload with a set of custom key-value pairs. You can include both of these types of payloads in the same message as well. Where FCM is for notifications from cloud to device, we'll now talk a little bit about Android notifications. One of the most useful features of a Wear device is the ability to see your phone notifications bridged to the wrist. With standalone Wear apps, both phone and watch may receive a similar cloud event and decide independently to display a notification for that content. This may result in duplicate notifications showing in the stream, one for the Wear side notification and one for the phone side notification. You can stop a notification from bridging phone side using the setLocalOnly API, but that would also prevent it from displaying on Wear devices that don't have your wearable app installed. Therefore, we're introducing a new API to disable notification bridging only when the Wear app is installed on the device. By adding the notification bridge mode metadata element to your Wear apps manifest and setting it to no bridging, phone notifications will be ignored and not displayed in the watch when your app is present. Another API we're adding for Android notifications is the ability to link a phone side and a Wear side notification together so they dismiss at the same time, even if they were posted independently. This is useful if the content is for the same topic. The new API, setDismissalID, allows you to tag notifications on both watch and phone as dismissing together. This API is now available in the Wearable Extender class in Android N's preview support library. You can see how to add a dismissal ID string to a notification here. If your app on watch and phone each post a notification with the same dismissal ID, and the user dismisses either one of them, the other will dismiss automatically. A fourth area of focus for standalone Wear apps is how to get them installed and distributed. And we have some exciting changes coming in Wear 2.0. In Wear 2.0, Wear apps are downloaded directly to devices from Play Store. You no longer need to bundle them inside of your phone app. We are expanding the multi-APK feature of Google Play Developer Console to support Wear. Multi-APK allows you to publish separate APKs for your application for different device configurations. You'll now be able to have one or more phone, tablet, Wear, or other APKs in your Play Store listing at the same time. This change brings with it a number of benefits, including smaller phone APKs, a decoupled release process where your phone app and Wear app can be updated independently, support for per-application APKs when using per-architecture APKs when using native libraries, and more. To give you a taste for how multi-APK support will work for Wear, here's an Android manifest file for a typical wearable app. It includes a uses feature element set to hardware type watch. Because of this feature is strict, APKs built from this manifest will target only Wear devices in Google Play. Similarly, APKs built without this restrict will not target Wear devices. Wear device targeting can be combined with other criteria, such as SDK version, screen resolution, and CPU architecture. Let's walk through an example of how this may work in Google Play Developer Console. Say you've built both a phone APK and a wearable APK for your application in Android Studio. You then go to the Google Play Developer Console to upload both of them one at a time. You'll need to select Advanced Mode in order to have more than one APK in your application at once. After uploading the wearable APK first, we'd expect the list of supported devices for this application to be just watch devices. And by clicking the supported devices link, you'd be able to verify that only watch devices are shown. Now you upload the phone APK to Developer Console. The set of supported devices for this app has now increased to over 2,000 and includes phones. You'll also notice at the bottom of the screen that there are two APKs listed, one for watch and one for phone. The watch entry shows the feature restrict being present. Multi-APK support requires that you use a unique version code for each upload APK. In this example, the wearable APK was set to version code 2, while the phone APK used version code 1. Since Wear 1.0, Android Studio and Gradle have provided a very simple way to automatically bundle Wear APKs inside of phone APKs, as shown. You can turn this bundling off by removing the Wear app project dependency from your phone app's Gradle file while testing standalone apps. Multi-APK support for Wear 2.0 is coming soon, and we'll have more announcements on this over the summer. For now, simply sideload your application, your standalone Wear app, directly to your device for testing. Now I'll hand it over to Kenny to show you a couple examples.
OK, so let's put together all of the principles that we've just talked about and see what it'll be like to make standalone apps in Wear 2.0. We'll start with a chat app. And for this example, I'll assume a couple of things. I'll assume that you've already got an existing Android phone app. You are at kind of production quality, and you're public, and you have a fairly big user base. OK, so going from the top, key use cases are pretty obvious. The key use cases are going to be send a chat, receive a chat, basically. So that's going to require a bunch of different activities, login, list of friends, chat settings, et cetera. But because we're really trying to streamline interactions, you want to make sure that every UI that you build is in service of those key use cases. OK, so now let's talk about how we're going to build it. We've already got a phone project in Android Studio, so we're going to create a second flavor of our build. So this new flavor is going to be our wearable build, and it will start out the same as the phone. But we'll factor out the shared code between the two builds. And we'll build a shared library that both of those will use. So the first thing that we'll put into that will be our entire REST client service that we had built for the phone, so that both our wearable and phone are now able to talk to the cloud. So on top of that REST client, we're going to build some activities. Now, we're going to use material design for Wear, and I'll just hand wave through that, because the next talk in this room at 3 is about material design for Wear. So now we have a wearable app that uses those material design principles and can talk to a web service on the watch. So we're already pretty far along in building an app. But this app is not always going to be in the foreground. Messaging is really driven by notifications. So the next thing that we're going to add to our app is we're going to register it for FCM. So once we register for FCM, we're going to start getting pings from FCM whenever we need to show a notification. Because we're now getting pings, we'll disable bridging so that we don't get bridge notifications from the phone at the same time. When we show a notification, we'll use the new messaging style for a notification, which will show a really nice presentation for that message on the user's watch. Now, when the user taps that reply button, we'll use a content intent, which will allow us to start a reply activity that's custom designed for our app, and it meets our exact needs. OK, so we're going to have to make this user sign in. There is no, well, we could make an anonymous chat, but we won't. That means we're going to start with a basic sign-in activity. So we're going to have a username and password as our 2 blank boxes. But then we're going to add some fast sign-in features. So I'm going to assume here that I already had an existing OAuth web service. And since I have that, Smart Lock is a really good option because it integrates well with an existing auth service. Another option that I can add is OAuth URL, which will allow me to log in via a couple of changes that I'll have to make to my web flow. So now let's start thinking about how to make this app work really well when you've got your phone. We're going to coordinate dismissal by sending a notification ID inside the FCM payload for each of our messages from FCM. And then we'll add that dismissal ID, we'll add the notification ID as a dismissal ID to both the phone and the watch notifications. So then when I swipe away a notification on one, it will swipe away on both. So now we have a great wearable chat app. It works well with the phone, but we really need to test it on all the watches we can get our hands on connected to both types of device. You really have to make sure that your app is working well on both Android and iOS connected watches. And then the next thing that you really want to do when you have an existing app is to profile your REST services. So probably in this app, what we're looking for is data that's not being used on the wearable. And there are a couple of options we have if we find big chunks of data that aren't actually being shown to the user. One is that we can cut it out entirely if it's not being used on the phone either, or we can make new requests and responses that are specific to the wearable app. So sort of cutting out that data and only showing the wearable what it needs to know. When we're ready to distribute, make an unbundled wearable APK, set up the manifest as Griff described, and upload to play. So now we've built a pretty easy chat app based on our existing phone app, and it works great in Wear 2.0. OK, go to another example now, a fitness app. So everybody has their favorite running and cycling app, and those are all pretty horizontal. So a new idea might be to go vertical. So I'm going to make a rock climbing app. And this is a new idea, so we'll start from scratch with no existing phone app, no existing web service. So since we're starting from scratch, we'll really be thinking about the wearable first, how people are going to use a wearable to track climbing, what kind of information they might want to see on their watch. So I'm going to assume here that there is some black box sensor magic that somebody is going to build in order to make this work, because I'm a PM, and that means that I don't have to code, so thank you, engineers. But what we do want to make sure is happening is that when we're processing sensor data, that we're as battery efficient as we possibly can be. Because whenever you're processing data, the processor has to stay awake, and that is burning battery. So what we really don't want to have is the user gets halfway up that rock wall, and then their watch dies. So once we process all the data, we're going to store it locally in a SQLite database in case the user isn't currently connected to the network. Now, we're going to build some new activities with material design for Wear. We're going to support always on, which is something that we released last year and allows apps to keep running in the foreground when the watch goes into ambient mode. So if you want to find out more about that, you can still check out last year's talk on YouTube about always-on apps, and those principles will still work in Wear 2.0. So at this point, we have a wearable app that's storing data locally, and it's a cool app for climbers. What we might want to do next with the app is start storing that data in Fit. Now, Fit can give us a lot of interesting stuff. We can get biometric data from the user, like their height and their weight and other data that they've entered. And we can also write into the Fit platform our rock climbing sessions so that the user can see all of their fitness data in one place. And I can verify that Fit has an activity type for rock climbing. So we're already halfway there easily. So far, our app is a generic, anonymous app. But if you're not a generic lumberjack and you're a climber Jane, you want the user to log in so that you'll be able to identify that user in the future and also bring that user online onto the cloud. So Our app can offer a good amount of value without a login, so we're going to make login optional and defer it to when the user wants to log in. And when we do ask the user to log in, we use fast sign-in flows, such as Google Sign-In, which is easy because if I'm starting out from scratch, I don't have an auth service, I probably don't want to deal with all the requirements of figuring out how to do an auth service, so I can just let Google do that hard work. OK, so now we're logged in. That means that we can write data to the cloud. What you want to remember here is that although watches can run standalone apps, not every watch has cellular, which means that not every watch is going to be continuously connected to the cloud. So whenever you're writing data to those two sources, locally and remotely, you want to think about a sync. So you want to make sure that they're eventually consistent on both the local store and the cloud. So this diagram is getting pretty busy here. But let's say we want to throw the phone in, and how do we tie the phone into the party? OK, now, I think there's a pretty easy first step. This is, again, my PM speak. I think it's a pretty easy first step, which is basically just to do everything that we just did on the wearable. But now, since the wearable's writing all this data to the cloud, we just need to write the same thing on the left, on the right, and then we're done, right? We have a phone app that can now read and see everything that happened on the wearable. But what would be even cooler is if I could hand my phone to my belayer while I'm on the wall, and my phone could stream real-time data from my watch down to my phone, and my belayer could be checking out how my progress is going. So if I wanted to do that, I would use the data layer APIs. And particularly here, probably the messaging API is a good choice because it's very low latency. OK, so as before, test on iOS, test on Android. Profile. So there's probably less to do on the web services side here, since we're sort of starting from scratch. There's probably not a lot of cruft sitting in the web services. But where you would want to focus here is on how much processor that you're using. So make sure that you're not going to leave them hanging. Oh, wow. That's the first time I tried that joke. Last, we'll set up an unbundled APK and upload it to the Play developer console as before. So those are just two examples of how you'll now start to build standalone apps in Wear 2.0. So just to recap, 3 easy things to remember about why you want to build standalone apps. So first of all, standalone is phone independent. It allows you to free yourself in any situation during the day from the phone and still be able to use those apps on your wrist. Next up, standalone apps are built like phone apps. So they use phone app architecture, and all of those skills that you've learned and honed apply to the wearable apps that you're going to build. And then finally, standalone apps work with both Android and iOS phones.
If you like what you heard today and can't wait to try it out, you can. Just go to g.co/wearpreview. You can find out about how to get the Preview SDK, device images, and more information about the new APIs we're launching. In addition to the developer preview, we also have a few other sessions that you should check out. The next session in this very room is about how to build Wear 2.0 apps with material design. You can also catch up on YouTube if we've missed anything. One of the main reasons we are doing a developer preview is to get your feedback. So if you have any bugs or API suggestions, please go to g.co/wearpreviewbug. We also have an Android Way developers Google+ community where you can discuss with your peers. The URL is g.co/androidweardev. And with that, let's go to Q&A.